Alrighty. Oh, you still can't see the screen. Let me click this button. Hey, now you can see it. All right. Well, welcome back from the midterm. Went okay? Was pretty easy. Okay, that's good. That was the plan. Again, just a checkpoint here. Um, we're going to move on to new stuff here, which is very exciting. Arrays and vectors, and the next project. We'll see how far we get today. We might not start the next project till Wednesday. We'll see how far we get with arrays and vectors here. Oh, that's why you asked, because we have 2 weeks for this chapter. Okay, I am a little slow still. I've only had a little bit of coffee. I need more. Yeah, okay. So chapter 7 won't be due until the 10th then, because we're spending 2 weeks on it here. So let me go put that in here. So that's chapter 7. We do on the 10th. Thank you. Sometimes I do dumb things. This is chapter 7. And we'll put that out till 10th. I think I got your other zyBooks scores in there. Uh, submission, no submission. There we go. All right. If you want me to go back to some of the previous chapters and rescore them, I'm open to the idea. Um, if I give everyone like 1 or 2 chapters to rescore, does that seem pretty fair? Okay. I'd rather not rescore them all, but if you want me to rescore 1 or 2 of them at some point, I'm open to that. Again, it's for your benefit that you're just reading the textbook, doing the textbook stuff here, and following along in class. So we've got chapter 7 we'll do chapter 8 and chapter 9. So we only have a couple chapters left, which is pretty cool. We'll get to objects and classes. And then for pointers, we don't go crazy deep into pointers. We'll do all the pointer stuff, but next semester in 200, you'll do a whole bunch more with pointers. So it'll be a little bit of fun. We've got our break, review time, and final project work time. We can get that hopefully finished again by then so you can focus on your other final exams, and that should go pretty well. So let me pull up Visual Studio. I'm sorry? They don't have me on the schedule for it yet. So usually if they add another section, then they'd be like, who's free? And I can say I might be able to teach it depending on the time. Because the winter schedule is out now, if you go look. So this is week 10, right? 10, it says arrays and vectors. Now, definitely a little biased. I really don't like arrays, and I really like vectors compared to arrays. Some people really like their arrays, and that's fine. It's not terrible here. They're just a little bit more inflexible when you try and use them. Is really the entire reason I don't like them, because I'm all about things being easy. So if it's difficult for me to use, then I'm going to avoid it. All right, so we got our namespace. We don't even need this line. So the whole idea with an array is now we can finally hold more than one of something. That's really all it lets us do here. So instead of saying if I wanted to have 5 different numbers, I don't need an int for number 1, an int for number 2, an int for number 3, an int for number 4, and an int for number 5. Right? I can say, hey, I want a place to put 5 integers here, and we can use an array to do that. So we can say I want an integer array called numbers. Now we have to tell it, hey, I want 5 numbers here. Oh, goodness gracious. I'm on the wrong side. Numbers. Sorry. I always get mixed up on which side these square braces go on. So we use square braces here to reference the index. Now, we're going to start counting at 0 because that's how all normal people count. So we always start 0, 1, 2, 3, 4, right? And that's how you get to 5 things, right? Doesn't make a lot of sense. It's okay. We'll get there. We're going to do it all the time. So we always start counting with 0, and there's good reasons for it. So if I want to access one of these numbers here, I'm going to say, hey, numbers, and then I use my square braces to say index of. That's how we kind of say this in English. So it's numbers index of 0, and we can assign, hey, the number 42. And I can say, hey, numbers at index of 1, numbers index of 1, let's assign 77. And numbers index of 2, let's put in 100. Numbers index of 3, we can put in a 0. Doesn't really matter what we put here, right? Just throw some numbers in. Numbers index of 4, let's put in how about a 6? Okay, so I have room to store 5 integers here. And I can then go assign individual values to each of those 5 places using this index notation. So we always start counting with 0. So the first position is index 0. Now, this lets us assign. We can also use that same notation to read them. So if I want to do output or do something with it here, I can say, hey, I want numbers index of 2, right? And we can just do arithmetic right in here. Let's double that, right? So numbers index of 2 says, hey, C++, go out to that numbers array, go to the second index, read the value that's there. Just like it's a single variable, it will go get the value that's stored there. We're just saying, hey, go to the array at the second index, right? So it's like, go to this spot and then up a little more. Now, the whole reason why we start counting at 0 is the way all of this is calculated is some cool little speed up memory magic. So remember when we store a value, the computer, we have to go out and ask our computer, hey, I need a place in memory to store it. And we know its memory address, right? It's somewhere in my computer's memory. Here's the address to it. And we go look it up by address. With an array, we get a chunk of memory that's 5 times the size of an integer, right? If our integers are 32 bits, right, for integers, we get 5 times 32 bits of memory in one spot. So it's a contiguous block of memory. And what we get to do is if we want the 0th index, the first item, it just reads an integer at that memory address. It says, okay, here's where the memory address starts. Read 32 bits. That's your integer. Hey guys, yes, if you're going to talk, go out in the hall, please. Thanks. If you want the second index, it says, okay, I know the size of an integer is 32 bits. Let's take your starting address and go up 2 times 32 bits. And it just shifts this space and this space over, and it reads right at that location. If I wanted an index or an array with like 1,000 indexes, we can do that. It'll get 1,000 times 32 bits, that chunk of memory. I can read index 27. It'll take an integer times 27, offset that from the start address, and go read it. So we get immediate access to any location, right, based on its index. So that's why we always start at 0, because the first number is actually written right at that location in memory. So there is no index 5 here. So bad stuff happens if you try and use index 5. Because we never put anything there, we're going to get garbage, right? What's ever written here, it's not part of the array. So if we try and just go and access the value here, excuse me, C++ is going to say, okay, sure, it's some garbage number. That's not helpful, and we never even got a warning that, hey, you shouldn't have done that. Now, we're getting a warning here because Visual Studio knows, hey, you said it was size 5, you're trying to access an index that doesn't exist. But it's not giving us a very nice notation here. It's saying, hey, the readable size is only 20 bytes, but 24 bytes might be read, right? Because a byte is 8 bits. So a 32-bit integer is 4 bytes, and it knows, hey, we only did 5 times 4 of those. We only had 20 bytes. Now, if you don't know that stuff off the top of your head, you're like, why is it 20? I told it 5, right? Like that sort of stuff doesn't really make a lot of sense. It's not a very helpful error. But if you like keeping fun facts in your head and you have nothing better to do, you probably remember an integer is 4 bytes. And oh, 5 times 4, that's where it gets the 20 from. And that you're reading 24 bytes because we're trying to get out a 5th index, which is really the 6th item, right? 6 times 4 is 24. So saying, hey, you've read 24 bytes, but we only ever used the readable size was 20. But it works. So lots of bad stuff can happen if we're not careful in C++ because it lets you shoot yourself in the foot, right? There's no protection here to not let this program run and you're going to do a bad thing. So if you're not careful, you're like, oh yeah, I have 5 items. I'm going to go read index 5. I want the last item. And you've done a bad thing. Right? The only thing we get is Visual Studio saying, hey, dummy. But it's a really bad error. It's not very helpful. And this is one of the reasons I don't like arrays. But again, it's okay. It's not the end of the world here. It's totally workable. Now, we'll just let that be garbage. That's okay. If I try and assign to it numbers of 5, and we put a number here, let's say like put a 20 in that location, and now let's see if we can read out. Now we get a build error. So this one here is a forcible error Again, though, saying, hey, its size was 20, you did a bad thing. But it's not a good error saying, hey, your index is invalid. Right? You have to do the arithmetic yourself to realize what's actually happening here. So if you assign to it, it stops you. Your program won't even compile and run. But just reading from it, it lets you read garbage. Okay. So thankfully, this one won't compile. So I'm going to leave that commented out so it'll work for us here, and we don't need to read it again because we already did that once. Okay. Now, the downside of arrays, right? You'd be like, oh, hey, it's number, I want 5 here. What if we wanted to ask the user? If I had an int for a size here and we said, see out, enter a size, enter, I don't know, the number of numbers you want to store, and an end line. And then if I said, hey, I want more numbers, or so this is my integer array of, I don't know, user numbers, size of size here. Well, that doesn't work. It says expression must have a constant value. The variable value of variable size cannot be used as a constant. So what happens is when you make an array, the size has to be known at compile time. So when we hit our compile button or our build button here, right, build and compiles, when you hit run, it has to compile first here. You can't have an unknown sized array because it doesn't know where everything's going to go. It doesn't work. So I can't ask the user, yeah,
What if you initialize it to zero?
I'm sorry,
When you initialize a variable, is equal to zero.
we could do that, but then if I see an on size, right? So as soon as I'm doing the cin, it knows that it's variable. It knows that the value has changed based on something else. So if I started at 0 and never ask the user, yeah, we can use size. Size, no? Is it? Oh, I have to tell it it's constant. It's got to be greater than 0. Sorry. A couple of different errors. It doesn't let you do a size 0 because that's useless. So you have to use the constant modifier here so that you can't go change it after the fact. Right? And if it's constant, then I can't go cin on that value here because that part fails because it's constant. So there's a couple different protections here to make sure you can't use a variable size here for your arrays. These are fixed sized arrays. Right? They're very fast, and that's why people like them. They're very memory efficient. They just give you a little chunk, you know what size they are. You can do things with them there. Um, excuse me. Now, the other fun thing we can do is we can use arrays in functions. So I can have some sort of function like an int for total, or I don't know, sum of array, given an integer array called, I don't know, numbers here. So if you give me an integer array, oh, is it on the other side? Numbers? I hate trying to remember where these things go. There we go, numbers. Now I can go through and get the sum of these, so this array here. Now, the hard part is I don't know what size this array is here. But we've got some shortcuts, so we can do some quick notations. I can have init for I don't know, we'll say sum. It starts at 0, and then for int number in numbers. Uh-oh, I need something. It's not working here. I can't just loop through this value because it doesn't know what size it is. So you have to pass it an int for the size here, which is obnoxious. And now I'm not going to use this sort of loop. I can use an int, a regular for loop. I might say, hey, the index starts at 0. As long as my index is less than size, take my index plus plus. Now, most normal people just use the letter I here. I hate that. And it just drives me crazy. I'm always going to spell out index here because I'm just obnoxious like that. So everyone else you see will just use the letter I there. That's fine. I'm always going to use index because it's more clear to me. I can type a couple extra letters. I don't mind it here. Um, and I get really confused between I's and J's. And sometimes when you have a loop within a loop, they do an I and then they do a J, and then I can't tell the difference at all, and I just feel stupid. I don't really like feeling stupid. Not a very pleasant feeling. I get that enough. So I'm always going to spell out index. So I can take my sum and I'm going to add to it, right, my numbers at the index here. Right, so the numbers array at the index. So if you give me the array and you tell me what size it is, I can go loop through it, right? I think there's another way. Was it C++ size of array? Let's see. There's a size of thing here. Yeah, okay, so you can do the size of here, which is kind of fun. Let's just steal this one here. There's a size of function that I think this one works here. Let's see, so size of numbers divided by the size of an integer. Let's try that one here. So if we can do this without passing size here, we'll get, I don't know, how about the array length? We'll do that. So you can ask C++, hey, how many bytes of memory is this thing using here with this size of function? Which is kind of cool. So, hey, tell me what size it is. Uh-oh, size of a pointer.
Sure. Okay. Remember. You have to also use it for that word.
Well, we're going to see if this one works. So we'll try and pass it here. So I think the sum should be, let's use better numbers here. 1, 2, because I can't add in my head right now. 4 and 5. All right, that one should be a little better, right? That is 15. So let's see if we get out 15. So if we get, we want to see out um, sum of array given my numbers array, end line. Let's see if that'll work. Uh-oh, build errors. Sum of array needs to return it. Okay, we just didn't return sum. There we go, return sum. Let's try that. Uh-oh.
You didn't convert things.
We didn't, I thought we outputted it, sum of numbers. Let's see. I think this warning here is telling us what the problem is. So we get to here, and we're going to try and compute that array length is 2 is not correct. So size of numbers didn't give us the right value here, which is sad. Doesn't actually know how long it is here. So we got to go back and pass size. So if we were doing this in the main function, we probably could get away with it here. Once we've passed it, it does a funny thing. It mentions pointers. We'll get to that later. Don't worry too much about it here. So we'll stop this and go back to size. So we'll take an int for size. And we'll loop like this. Let's give that a try. See if we get 50. Oh, goodness, build errors. Oh, I didn't pass it here. That's right. Nope. There we go. Numbers and 5. Because it's size 5. Now we get our 15 back out. Life is pretty good. What happens if we give it 6? We got garbage plus 15. Right, here's the garbage value. That was at index 5. And we added the 15 actual sum to it. So again, it's not great here. Trying to deal with indexes and sizes. Yeah.
Every time you have to put the thing here, put comma and then number and
If you're passing an array to another function, because the function is going to have no idea what size that array is. So you have to tell it. Okay. So arrays are kind of stupid. I don't really like them. They're super fast though, and people love them all the time. But that's fine. Um, what I like is vectors. So you had a little bit of exposure to vectors. Sorry, we got a little off track there with vectors and files and whatever we were doing there, but we'll come back now. So a vector, same idea as an array, but it's resizable and it knows how big it is. Amazing. So you can make a vector now of numbers. So the syntax is a little funny for vectors though. So we're going to say, hey, I want a vector and then I use greater than and less than here. And inside of that, I say it's an int. So instead of saying integer array, here it's a vector of type int. This will make a whole lot more sense next semester. We'll get into doing these sorts of things with the braces ourselves. Don't worry about it right now. We'll just say, hey, it's a type int. You can put any type you want here, which is really cool. You can have a vector of anything, but it just has to all be the same type. Right? Same with the arrays, they're all the same type. Right? You can't mix and match doubles and integers and strings and floats and things, right? They're all one type here because it has to know how big to size that array, how much memory it needs. So it needs to know the type to know how much size it needs. So a vector of integer, we'll call this my better numbers here. Now, when we make the vector, we can give it a size. So I can say, hey, I want to put 10 things in this vector here, or we can leave it empty. Right? Either way is going to be okay. We've got options here. So we'll do one more vector of int resized numbers, and we'll just do 5 here. Okay. Now with vectors, you've got two choices for how to use them here. And I'm going to recommend you don't use the array notation, right? So we can say, hey, I want my pre-sized numbers index of 0 and assign it 42. Perfectly fine. You can do that. Or you can say, hey, I want my pre-sized numbers dot at index of 0 and let's do index of 1 here and assign a 77. So the at notation is much better. Not everyone likes it. It's okay. I really like it. You can use the array notation. You can use the at notation. Now, if we mix and match here, right, we'll just keep on going. So let's do index of 2, index of 3, and we'll just do 4. I'm sorry, 4 and 5, right? We don't have an index 5. Does not exist, right? We only have 5 spaces, so there is no index 5. We have 0, 1, 2, 3, 4. Let's go back. What do we do? 100 and 0 and 6 or something. And let's put a 7 here. So let's go try and put some values in here. When we run it now, it breaks. So it still compiles and runs here. So it lets us compile, but as it's running, we get a standard exception out of range at memory location. So this will just hard stop that, hey, you tried to do something at an invalid memory location is a bad index. And still not a great error message that we're working with here. It's a bad index. So it just stops working here and crashes. This is not ideal, but it doesn't let you do dumb things here. So instead of setting, how about we just try to get a C out? Let's just go get this value. So you can use this at notation for setting and for getting. Just a little bit weird, but that's okay. So you use end line. There we go. At to get the value for setting or getting, just like we do with our braces here, our indexes. Right? Go set the value or go get the value. Works the same way here. So same with the at function here. So if I try and read the value at 5, it crashes on me. Now, weirdly, I prefer this because I'd rather not get a garbage value. I'd rather have my program crash and tell me, hey, you did a dumb thing, rather than just continue on with garbage. Because if you're continuing on with garbage values, you might not have noticed you did a dumb thing, depending on how big your program was. Like, and if you're doing anything that actually matters, using a garbage value screwed everything up, and it's not happy. So it's probably better for it to crash and be like, oh, okay, I need to go fix this here, right? So weirdly, I like the crashing here. So this gives us a crash. The program getting an invalid index. Now, that's with the at function here. If I use my index here, let's do this up above here. So hang on, we'll comment that one out for a second. And let's use our index notation. Still crashes, which is nice. So we still get the error checking with the at notation or the index notation here, which is fine. So we're just going to just abandon here. So both ways, we still get the checking here. Um, I just like using at. I don't know. I use this in other languages a lot, other sorts of functions here. Now, the other cool thing, we told pre-size numbers it was going to be size 5 here. Let me comment this one out. But if you wanted to add more values here, vectors are resizable. So we can go add more things. So I can take my pre-sized numbers here, and I can use this pushback function. So pre-size numbers dot pushback. Hey, let's go add a 7. Right? I know I started at size with 5 values here, but I want to add a 6th value here. Let's go push it back. Now all of a sudden this one's going to work for us here because we've added something at a 5th index. We've added a 6th item here. We added the 7. Right? So they're flexible. You can size them here and go and add items. You can remove items out of vectors. Now that one's a little bit trickier. It doesn't look like there's a place. So these are all the different functions. So you add a dot, you can see all the things you can do. You can get at, you can get the last item out, you can get the first item, the beginning. So this is actually an iterator. We'll get to those later. You can see the capacity, how large, how many numbers we can put in here before it has to resize. That's a little bit more complex. Uh, you can emplace, you can empty it to clear it out here. You can get the end, you can get the front. You can insert something at a given index. You can say, hey, I want to put something at index 3. and everything else will shift down, which is really cool. We can get its max size. You can resize it here. You can get the size of it. This is the most important one here. I can get the size of the vector. So if I want to go get my values out, right, or get the sum here, so let's go write another function. So this is a integer sum of vector here, given a vector of type integer, we'll call numbers here. I don't need to be passed the size because the vector knows what size it is. So I can use the same notation here. And instead of size, I can say my numbers dot size. And now that's a function call. So it gets a set of parentheses. It's not an attribute. It'll make more sense next chapter. Don't worry too much about it. But size needs parentheses because we're actually calling a function here. Right? So I can get the sum of all the values in that vector. So it's the sum of all those values is, and we can take the sum of my vector given my precise numbers. So what will that come out to be? 177 plus 48 is, oh my goodness, I'm just going to use my calculator because I'm feeling lazy. Sorry. 42 plus 77 plus 100. Numlock, 42 plus 77 plus 100 plus 6 plus 7. Should be 232 if we did it right. Do you think we'll get 232? Let's try it. We probably will. 232. Look at that. C++ can do math occasionally. It's halfway decent at math, right? So you don't need to tell it the size. And this is another reason I like vectors. They're just easier to use. Now, they're ever so slightly slower because they do all this other stuff that arrays don't do. They're a little bit slower. For everything we're going to do this class, for next class, probably even beyond that, no one's going to notice, right? But if you start doing something at millions of times scale, and you know exactly, hey, it's always going to be a fixed set of values, you can use the array and it'll be slightly faster. That's the sciencey part of computer science. Right? I like the software engineering. I like making things go beep boop bop. And my computer is really fast. Your computer is really fast. No one really cares for doing something 10,000 times if it's microseconds faster. It doesn't matter, right? But eventually it might matter when you do something at large scale. So just keep that in your back pocket, ever so slightly slower. Okay. So that's the basics with our vectors and our arrays. So arrays are fixed size. You have to presize them with a constant value. Vectors are not. You can add, you can remove. We'll get to removing later. I don't think we need to do that right now. We can save some stuff for next time. How's my battery doing? I've got 20% left. It's going to die pretty soon. That has not lasted very long. Really should have checked my backpack. I thought it was packed already, but I did a bad job of that. Um, so let's take a look at Zybooks real quick. Let's see how we're doing on all their chapters here. So our arrays and vectors. Not a super long chapter. I mean, it's got 15 pieces here, but not too much here. So vectors, iterate, iteration, going over item by item by item. The other cool thing, we don't even need to use this notation either. We don't have to get stuff out by index, right? We can use that enhanced for loop. So instead of doing it this way here, we'll just leave this commented out for a second. We can do the quick little shortcut and say, hey, I want for int number colon numbers, take my sum plus equals the number, right? If you're not setting values, if the only thing you're doing is reading, you can use this little enhanced for loop. So really this is like a read-only loop, okay? If I change number, it's not going to change it inside the vector. So I don't want to be doing any sort of arithmetic and expecting number to stay changed. Right? If you want to change the values, yes, we want to use the index notation where I can assign to a given index. And we'll have some more practice with that later. But both ways are nice. And again, this is just super fast and easy to type. And I like that. It makes my life a little easier here to just get the sum. Return, oops, I did not. There's a weird place for that comment. Huh, supposed to be there. Okay, that's why. Excuse me. All right, so we can return the sum, and life is good with this one here. Let's see. So, initializing. If you know the values here, so we just said, hey, this was a better numbers. We never used it here. You could just push back and push back and push back. So you can ask the user, hey, let's add some numbers, add some numbers, add some numbers. Just keep on going until you're done, because you can keep resizing your vectors. You can just keep adding stuff is great for that one here. If we know what the values are going to be here, so let's say, hey, I want it to equal 1, 2, 3, 4, 5. I can use curly braces, which is the weird thing here, but sure. So if I know what the values are ahead of time, I don't need to do it 1 line, 2 line, 3 line, 4 line, 5 lines at every index here. So you can use the initializer here. Initializer, make this faster than going by index. Okay. So this is, will give you, sets up with spaces for 5 values, where this one just says, here's the value of your values here. Um, Now, I think we can do that with our array notation as well. So if we did that of size, we'll just go back to 3 or something here, equals 1, 2, and 3, or I don't know, 20, 30, and 40. Okay. The notation, this initializer, works for both, for arrays and for vectors here. It's okay if you know what your values are. So again, it's not just an advantage to vectors. You can initialize this way so you don't have to do it one index at a time, but you've got that choice, right? Both ways will work. They're going to do the same thing for you here. So we can initialize them the same way. We can iterate through vectors, have multiple vectors, resizing vectors, hop back and get the back will give me the last values here using loops. We can compare vectors here, swapping, reversing a vector, uh, two-dimensional arrays and vectors is really fun here. We'll get to those in a while. Character arrays and C strings are the older style, how we used to have to manage strings. Right now we have a string variable. In the precursor to C++, we had C, which was not object-oriented. You had a C string, which is just a character array. So I had an array of characters, right? We said a string is really like an array of characters, a collection of characters. In C, they actually are actual array types here, and it does some funny things there. We've got a bunch of C string library functions we can use if we have to deal with C strings. Hopefully you never have to because they're miserable, but that's okay. Um, we've got some options here, and we got a couple labs we'll work through. So we got quite a bit of time, which is nice to work through some of these, but my battery's about to die here. Yeah, I'm at 16% now. It's going to cut off soon. Um, seen a little bit. I think we're in pretty good shape. Why don't we plan to meet back up Wednesday? We'll get through some more of this here. We can talk about our next project on Wednesday, and I'll have my power cord for sure. Then does that sound good? All right. I wasn't going to go over the midterm questions because I thought they were pretty basic. If you'd like to see them, I'd be happy to go over them with you. Um, can definitely do that. I can probably do it on the other computer here if anyone wants to see any of those. And then the solution to project 2 that was due this morning, right? We can go over that on Wednesday as well. I don't think I'll be able to get that done in the next couple minutes here before the battery dies. Uh, but hopefully that went pretty well with Hangman for everybody. We had our functions. Again, part of the goal was just here's using functions, passing things around with functions a lot, so we don't just have a bunch of stuff all chunked in main. And one of the nice things with functions is it can make main nice and small, right? And we can do our functional decomposition. I know you're going to throw that around at your Halloween party. It'll be really fun. You'll sound really smart. People will give you funny looks here. And we can make a big problem smaller and solve it much more easily here, one function at a time. All right, sound good? I'll see you folks Wednesday then.